So solids, liquids, and gases, this should be review. Here we have illustrations, a molecular view of gases. We see the individual, and this is, we're looking at water, individual water molecules spaced widely apart. Here, the distances between the molecules are such that intermolecular forces have very little impact on the behavior. In a liquid and a solid, the molecules are touchingly close. And so they are close enough that the intermolecular forces become significant. This is just giving us some details about this, the temperatures, the density, and the molar volume. I think the density is interesting. The density of ice is 0.917 grams per cubic centimeter, liquid water 0.998, and then for gas it's 0.00059 grams per cubic centimeter. Much less dense. Water and ice are very similar in density, but steam is much less dense. The big difference between liquids and solids, their densities are similar, molecules are touchingly close, is freedom of movement. So in a liquid, the particles have enough thermal energy to partially overcome the attractions between them, allowing them to move and slide around. In a solid, particles are moving, but they're stuck, so they're vibrating. And I've mentioned this before. Currently, you guys are in the solid state of students. You're sitting in chairs at the benches, and you're not moving relative to each other. And yet you're all moving, right? Breathing, jiggling your leg, taking notes, whatever. In lab, we have the liquid state of students where we're up and we're moving around. We're milling about the room. Are we any farther apart from each other? No, we're still confined to this room altogether, right? But we're moving relative to each other. So the state of matter depends on how strong those intermolecular forces are compared to the thermal energy. The thermal energy is like the agitation level of the molecules. How much is it moving, right? And if it's moving a lot, it can overcome stronger forces. So here for gases are going to have a low density. They're going to have an indefinite shape because the particles aren't attached to each other. They'll take on the shape of the container. It also has an indefinite volume. The gas will expand and fill its container. The intermolecular forces are weak relative to the thermal energy. And so they don't stick together. In liquids and solids, we have high density, but the shape is different. Liquids take on the shape of their containers, solids do not. Volume for both is definite. But liquids would have a moderate strength of intermolecular forces, whereas solids would have a strong intermolecular force strength. Liquids, because the particles move, they can take on the shape of their container. If you stuck an ice cube in an Erlenmeyer flask, it would just sit at the bottom, being the same shape that it was before. Gases are compressible. Liquids and solids are not compressible. So here, if we look at this liquid, we see there's really no empty space between the molecules. They're touchingly close. And so if we put pressure on the top of this container, we can't squeeze them any closer together. In a gas, though, there's a lot of empty space, and that space between the molecules there isn't air, it's nothing. And so when you push on this, you can push the particles closer together and compress the gas. There are two broad categories of solids based on how the particles are arranged, crystalline and amorphous, and I believe we've mentioned these before. So in a crystalline solid, we've got a well-ordered three-dimensional pattern. So here we see that there's a definite pattern to how these little green atoms are arranged. Amorphous means without shape, and so here the atoms are just all jumbled together. It's a solid, and so they're not moving relative to each other, but they're just stuck together basically randomly. So, quick question here. Which state of matter is compressible? A gas. Changes between states. We're familiar with a lot of the state changes. Most of these can be made to happen by changes in temperature. So water's convenient to think about. If we think about solid water, we call that ice. If we heat that up, we can melt the ice into a liquid that we call water. And if we heat it up further, we can make it evaporate or form a vapor. We can also go the other way. We can take a gas and we can cool it and form a liquid, condensing it. We can take that liquid and cool it some more and freeze it into a solid. So we're familiar with the changes due to temperature. When we have changes involving a gas, either liquid to gas or gas to liquid, those changes can also be made by changing the pressure, either with the temperature or independently of the temperature. So if you take a liquid and reduce the pressure above it, you can cause it to turn into a gas. If you take a gas and increase the pressure, this makes a little more sense, you can squish it together and make it into a liquid. Here's an illustration of a propane cylinder. LP, liquefied petroleum gas, it's mostly propane. And so here, the contents of this cylinder are under pressure. Under pressure, the propane is a liquid at room temperature. So here we have it shown as a liquid. There is a small space above where it's evaporating and forming a gas. And if we open the valve here and release the pressure, the propane here that's in the gas state will come out of the cylinder. And then more of the liquid will evaporate, and you can empty the entire tank that way. And so the gas you would direct to a grill and make some burgers or something. Another conceptual question. So this molecular diagram shows a sample of liquid water. Which of the diagrams below, A, B, or C, best depicts the vapor emitted from a pot of boiling water? So what's the difference between these three diagrams? In A, it looks like we have water molecules, right? And in B, it looks like we have oxygen and hydrogen molecules. And in C, it looks like individual atoms of hydrogen and oxygen. When you boil water, what happens to the water? It evaporates. It goes from a liquid to a gas, but it's still water. Right? It doesn't come apart into hydrogen and oxygen. It's still water. It's just that its relation to the other particles is different. The gas state of students is when class is over, we open the door and everybody goes off in different directions. Are you still you, even if you're not in class? Of course you are. You're just not with the rest of us, right? So which of these diagrams is the answer? A. Any questions about that?